Hello everyone, my name is Mina Fasihi and I want to talk about complex network description of phase transition in disordered classical and quantum Ising model. So to start that, I need to talk a little bit about thermalization and localization. As you may know, thermalization means over a long period of time, all microstates of the system are accessed with equal probability. So if you start from an initial state with non-uniform density, the thermalizing system relaxes toward the state where all lattice sites are equally populated. Thermalization requires that different parts of the system exchange energy and particle. So it means that this thermalizing system is conductive. But we can find system with insulating behavior, such as Anderson localization in non-interacting disordered systems, in which a disordered potential makes wave function become localized in some region of space and decay exponentially far away from that region. Therefore, some local details of the system's initial states remains in the eigenstate. This is very interesting because localized system can be considered as possible quantum memories. By adding interaction to Anderson localization, there will be a competition between disorder and interaction, which may potentially destroy localization. But there are strong evidences that localization can occur in highly excited states of interacting many-body systems, which is known as many-body localization. These kind of systems have properties such as failing ETH, area law entanglement instead of volume law entanglement in thermalizing system, and logarithmic growth of entanglement. Having these localized phases, there will be quantum phase transition between them, and network measures can be employed in detecting these phase transition, which is the goal of this presentation. So to show how we can use network measures, I present the simplest case, the well-known classical Ising model in 2 dimension, having this Hamiltonian and with J being the coupling constant and H being the Stern-Fock external magnetic field, we know a phase transition happens at t equal to 0.269. We can see it from the plots for energy and magnetization. If we want to map the system into a network, we need to consider every spin on the lattice as a node in the network. And then we need to make an interaction matrix or the adjacency matrix that gives us the relation between each two pair of nodes in the network. So since we don't have self-connection, the diagonal of this matrix is 0, and the connection between nodes are given by the correlation function. And as you can see, the second term of correlation function is nothing but the square root of magnetization, which we know that it reaches a constant value at different temperatures. So the behavior of the correlation function depends on this first term. And using correlation function as the connection between nodes, it gives rise to a weighted network. So having the network ready, we can run some network measures such as degree distribution, which gives us the probability of having degree k for any randomly chosen node. We can have the clustering coefficient, which tells us how many hubs are in the network or how clustered the network is. And we can have the shortest path length, which measures the shortest path between nodes I and j. These properties are known for some famous network models, such as Fatsis-Turgats or small world model, the Barabasi-Alberto scale-free model, and the Erdős-Renyi model or random network. So given any network, we can run these measurements and see in which category our network lies in. It can lies between some of these categories as well. And we can identify the behavior of our system. Okay, so we ran these network measures for the classical Ising case. And for degree distribution at temperature 0, since all the spins are aligned, the first and second term of correlation function would be 0. At higher temperature in paramagnetic phase, since the spins are distributed randomly, averaging over 100,000 of realization, which is the number of steps in Metropolis algorithm, makes these two terms very close to 0. The only non-zero probabilities for degrees are seen at temperatures around critical temperature. And as you can see, it doesn't have quite a binomial distribution nor a power law distribution, but it has a power law fat tail. Power law distributions are very important because of their property of being a scaling invariant. They can be seen in so many complex networks, such as in so many complex systems, such as systems that have fractal patterns or cellular automatas. All of them show power law distribution. So one of the ways to see if the tail of the degree histogram is really power law or not is to check the log-log plot. As it can be seen here, the left and right side of the log-log plot is well fitted to a line with chi-squared goodness of fit being of the order of 1, which indicates that our network shows some complex behavior around phase transition. I also need to point out that just looking at the log-log plot is not enough for determining if the tail is power law or not. And if we want to be sure, we need to run some more accurate measurements, such as maximum likelihood methods. Okay, if we look at other network measures such as clustering and shortest path length, and also mean and standard deviation of degrees. All these plots have a peak around phase transition, which shows the change of behavior in the network, which means that the network measures were able to detect the phase transition. The other case that we considered are spin glass phases. We know that the spin glass phase have some similar behaviors to MBL, such as breaking ergodicity and slow dynamics, but the origin of this unconventional behavior in spin glass phase is different with the MBL. These behaviors comes from frustration in spin glass phases, which makes the system into a random magnet in which both ferromagnetic and antiferromagnetic interaction coexist and compete. As it is shown in this picture over here. We know that below a critical temperature, the spatially random spin pattern is frozen. So to add disorder into the system, we need to define Jij by a probability distribution. So the probability for having J equal -1 is P, and the probability for having J equal 1 is 1 minus P. So for P equal 1, we have the antiferromagnetic phase. For P equal 1/2, we have the well-known Edwards-Anderson models for a spin glass. And for P equals 0, we have the ferromagnetic phase. There will be a specific P at different temperatures in which a phase transition from a spin glass to ferromagnet takes place. To be able to capture it by network measures, we need to consider the system in a temperature that the behavior of the system is known to us. We consider the Curie temperature or the temperature that the phase transition happens in the classical case. Then we decrease the value of P gradually to see at what point the network random behavior changes. So if we run the network measures for that, we see that for both plots for degree mean and standard deviation and average clustering and average short path length, and there's a distinct increase at P equals 0.1, which means that at this point the ferromagnetism has dominated the disorder in the system, and there's a phase transition in this point over here. So the network measures were able to detect that again. But I need to emphasize that this p-value would be different for different temperatures. So if we consider the system at a lower temperature, like temperature 0, we could find p equal this change of behavior at p equals 0.107. Okay, so since the dimensional quantum system can be mapped to a d plus 1 dimensional classical case, we consider the quantum Ising chain. In the work done by our group 3 years ago, in this paper, the adjacency matrix for quantum case was built using different functions such as von Neumann mutual information and Renyi mutual information, running different network measures such as density, disparity between centrality, clustering, average geodesic distance, and diameter. We can see in all these measurements that the phase transition happens at temperature 0 for j equal h. These are the plots for the adjacency matrix space, the network built based on the von Neumann mutual information. And if we consider the any mutual information for that purpose, we again can see the change of behavior at j equal h. We are seeing the same kind of behavior, and we can conclude that network measures were able to detect phase transition in quantum case as well. The results for the disordered quantum case is under progress. So, in conclusion, in this work, we showed that network measures are great tools for capturing complex behavior in both classical and quantum many-body systems. We showed that network measures were able to detect different kinds of phase transition, and we pointed out the role of temperature and disorder in generating complexity. For future works, we want to consider other cases such as the XY model, the pulse model, the Heisenberg model, and we want to use renormalization group method to see if the network's characteristics remains the same at higher orders. And we want to identify the generators of complexity in quantum systems and ultimately find the relation between classical and quantum complexity. Thank you a lot for your attention.